So applications of operational amplifiers, in that we are going to see one more application, Schmitt Trigger. So Schmitt Trigger, it is otherwise called as regenerative comparator or squaring circuit. So this is the Schmitt Trigger circuit. In the input side, one resistor is connected. It is a parallel combination of R1 and R2, and in the output side, one voltage divider network is there by with the resistors R1 and R2. By proper fixing of R1 and R2, we can get the proper square wave for an corresponding input. It converts the irregular shaped waveform in square wave or pulse, used to avoid unwanted triggering and changing state. It is due because that unwanted triggering due to the noise because of the large open loop gain. We can increase the gain by using the Schmitt Trigger circuit. If we adjust the value, that is minus beta open loop gain, that is equal to 1, that is loop gain, then the feedback voltage gain will be infinite, but it is impossible to bring the open loop gain into equal to 1 due to the supply voltage and the temperature variation. Because of this problem, there is a discontinuous will be in output voltage. So this exhibits a phenomenon called hysteresis or backlash or dead band or dead zone condition. Now uh, just we remind that upper threshold voltage means low to high, lower threshold voltage means high to low. So the entire this is the input waveform, this is output waveform. The entire uh, operation and the circuit operation is depicted in the transfer characteristics. Now let us see. The input is start from 0, and upper threshold voltage is fixed here, and lower threshold voltage is fixed here. This is the peak voltage of input wave, and this is the square wave, proper square wave for any irregular shape input. So let us analyze with the transfer characteristics. Now the upper threshold voltage is fixed here, upper threshold voltage is fixed here. Now slowly the signal is slowly increasing and decreasing, crossing the zero level, and decreasing, keep on decreasing and increasing. Likewise here also, the from the threshold, upper threshold level, it is slowly increasing and decreasing, slowly increasing and decreasing. So the intermediate hysteresis voltage can be calculated, upper threshold voltage minus lower threshold voltage. The transfer character is drawn between output voltage and input voltage. So if Vn, the input voltage triggers the output, then the output that exceeds a certain voltage level called upper threshold voltage and lower threshold voltage. If the Vn triggers, input voltage triggers the output voltage greater than upper threshold voltage or lower threshold voltage, it will be obtained by using the voltage divider network, that is R1 and R2. The voltage across R2, variable reference voltage, fed back to the input. The reference voltage depends on the output voltage. The output voltage is positive saturation voltage, means then the reference voltage upper threshold voltage. If Vin less than VUT, then the VUT will be depends on the R1 and R2, R2 divided by R1 plus R2 into plus Vset. Likewise VLT, R2 divided by R1 plus R2 into minus Vc, saturation voltage, negative saturation voltage. If input voltage is greater than upper threshold voltage or the lower threshold voltage, then the positive feedback eliminates the false output transitions. Because of the regenerative action, V0 switch fastly between plus saturation voltage to minus saturation voltage. Here ROM in the input side, which is approximately equal to R1 parallel R2, used to minimize the offset problems and compensate the input bias current. The hysteresis or deadband condition means the comparator with positive feedback exhibits a hysteresis. We already saw about that hysteresis. If Vin greater than VUT means output voltage will be start from positive to negative saturation voltage, and if Vin less than VLT means the output voltage will be calculated 2R2 divided by R1 plus R2 into positive saturation voltage. It is almost hysteresis voltage. So the reference voltage is 0, means the output voltage will be equal to negative lower threshold voltage. The output voltage that is equal to R2 into V saturation voltage divided by R1 plus R2. So the inclination theta will be calculated by the ratio of upper threshold voltage divided by maximum voltage. Sin theta, that is calculated sin theta, that is equal to upper threshold voltage minus divided by Vm. So this is the perfect output waveform, input and output waveform. So let us, the upper threshold voltage is fixed here. When that time output will be in the positive saturation. If output is slowly increases and crossing the lower threshold level, in that time it will be, output will be in negative saturation. So keep on decreasing and crossing the zero level, means the output will be in positive saturation. Again this process will be repeated till we are getting the entire input voltage.